Oh, no, it's okay. Thank you. How does this work? Thanks. Okay, I'd like. All right. Anyways, thanks so much. I'd like to thank the organizers for giving me the opportunity to present our results on this. Anyways, so my talk today is going to actually outline a series of neutron inelastic scattering results on this material here. And hopefully I'll show you what I mean by soft harmonic phonons and relaxational dynamics at the end of this talk. I'd first like to thank my collaborators in this effort. So first of all, none of this would be possible actually without the tremendous effort made by Ian Swainson in terms of crystallography and materials preparation. He did all this work while he was at the NRC in Chalk River, the National Research Council. He's recently moved to the IAEA in Vienna. You'll see that actually to piece together a story about the phonons and the dynamics in the system, actually we had to cover quite a dynamic range in terms of neutron instrumentation. So we had to visit a number of different instruments to do this study. So I'm really indebted to actually all the support we've gotten from a number of facilities. So first of all, from Margarita Racina and HZB Berlin, where we took advantage of the neat time of flight machine. And also Lambert van Eck, who's now at actually Delft University, and his support at the ILL, where we used backscattering and the thermal time of flight machine. And I'll also be showing you some work done at ISIS using, particularly performed at higher energies, done on the MARI direct geometry spectrometer. And this effort was supported both by Stuart Parker and John Taylor. And also Stuart performed some cast-step calculations that really kind of helped guide the experiments and also the interpretation. And I'm also indebted to a couple of funding agencies who helped support this work. I should emphasize that the small print here is actually for the universities of Scotland. So this is the Carnegie Trust in Scotland. Okay, so this is the outline for my talk. So first of all, I'll be giving a brief introduction to this strange compound that I'm going to be talking about, methyl ammonium lead bromide, and in particular talking about the structure of this material, particularly some of the electronic properties, and in particular, what is behind all the recent interest in these materials. And then actually I'm going to go on and talk a little bit about neutron scattering and actually what I think neutrons can really add to this problem. You might think, based on this motivation, that neutrons really doesn't anything really to add to this story or to actually contribute, but hopefully I'll show you just through a few slides that actually it really can help us understand these materials. And for the rest of the talk, I'll be talking about neutron results. And first, I'll be talking about the molecular motions. You'll see that the structure contains of basically two bits. One, this molecule, this methyl ammonium molecule, and it's sort of stuck in this framework. So there actually is two sets of dynamics that we need to understand and probe in this system. So first of all, I'll be talking about quasi-static. Now, I put it in quotation marks because even though it's near the elastic line and it's very low energy, actually it really is an inelastic process. And people call it quens and quasi-elastic scattering, but it's really inelastic. So anyways, that's sort of a bit of a discussion about terminology and semantics. And then, so that's dealing with the molecular motions. And then I'll be going on and talking about actually the dynamics of the framework lattice, this lead bromide framework, and then finishing up with some conclusions and summary. Okay, this is actually some work here actually originally done by Ian Swainson back in 2003. And I showed this slide actually because I think it provides a very nice illustration of the structure and also a summary of the phase transitions involved in this material. So the structure contains basically two bits. It contains this lead bromide framework, so it contains a lead ion surrounded by an octahedra of bromine. And actually there's analogous materials, and I'll talk just very briefly about where you can actually put chlorine and iodine on this site. And this octahedral framework, actually within it is this linear molecule with one end is a methyl group and the other end is actually an amine group. Now, in this case, they actually deuterated the study for this particular work. This involved neutron diffraction, and I'll be saying a few words about why you might want to actually deuterate it later in the talk. But anyway, so the structure contains basically two bits. It contains this lead-bromide framework. So you got lead in this octahedra, and then you have this molecule that's kind of trapped in the middle and interacting via van der Waals forces. And this system actually goes through 3 structural phase transitions, which are actually plotted here. So this is a plot of spontaneous strain versus temperature taken from this plot. So this is done with neutron diffraction. And at low temperatures, it has an orthorhombic unit cell. And then at around 150 Kelvin, goes into a tetragonal phase. And then finally, at high temperatures, it goes into a cubic unit cell up here. Interestingly, this particular system has been studied for quite some time. I think there's even a paper by Wyckoff back as early as 1928. But this is some interesting work, actually, I think that summarizes some of the critical properties in the phase transitions, done actually out of a group in Dalhousie, actually back in 1990, and is published in the Canadian Journal of Chemistry. And what they plot here, they did a number of things. They did heat capacity on a series of compounds by varying bromine, chlorine, and iodine on this site over here. And they also did some X-ray diffraction. But I just wanted to point you to this part of the view graph here. So this here is actually a graph I took from their paper. So this plots heat capacity as a function of temperature. And you can see basically there's 2 clear phase transitions. And this is exactly what was found in the diffraction paper. So down here you have your orthorhombic unit cell. Here you have your tetragonal cell. And then up here you have your cubic cell. Now, to the people who sort of with keen eyes might notice that this isn't actually one peak here. There's actually split into 2. So there's actually another phase transition. And this intermediate phase going from the orthorhombic to the tetragonal phase is a bit of a mystery. I think at the moment there is some consensus from diffraction that it's some sort of incommensurate phase, but at least to my knowledge, and I might be wrong on this, and if anyone has comments about it, I'd be really interested to hear that no one's actually solved the structure and worked out what this intermediate phase is here. So anyways, what this plots over here is actually, this group also did X-ray diffraction work at room temperature. And the one thing they pointed out was that when they actually tried to solve for the, basically the molecular positions, or they looked at the electronic densities of states from their diffraction data, they actually found it was pretty featureless. So they postulated based on this that the molecule actually up here in this framework was pretty isotropic. It didn't really seem to have any well-defined structure or orientational order. So I'll talk a little bit more about that later. As I pointed out in the last slide, I just wanted to point this out as a comment. They also, as well as studying the bromine version, also studied the iodine and the chlorine. And basically, the phase transitions are very similar. Now, the chlorine version, the cubic transition, is actually shifted a bit, but the iodine version shows roughly the same behavior as the bromine. But anyways, these are sort of being fairly well characterized. Now, in terms of this conference, actually, it's interesting. I won't talk much about, actually at all about this for the rest of it, but the interest in terms of ferroelectricity has come from basically the orientation of this molecule within this lead bromide or lead chloride framework. And it's been thought that there are certain phases or ferroelectric phases in these materials. But the thing that's really driven the interest in these systems is actually, it turns out, their photovoltaic properties. That's been driven by, I guess, a couple of things. First of all, the efficiency of these compounds, and also they're fairly simple to. Also, it's fairly straightforward to make thin films of them, apparently. So in terms of applications, these materials, it's been a lot of interest in that. Now, here they quote some efficiencies. Now, it's always useful to have a benchmark no, sorry, I guess this is to actually figure out how these materials compare to conventional materials that people found. So actually I found this paper quite useful in that. And what they plot here is the power conversion efficiency as a function of year. And so they plot sort of some conventional materials. And up here are these methyl ammonium, lead iodide, lead bromine type materials. You can see there's a big jump in efficiency that's associated with these things. So this has really driven a lot of studies and a lot of interest in these materials of late. Associated with the photovoltaic aspect, actually, just in terms of semiconductors, which is of course related to the photovoltaic properties of the material, the semiconducting properties are extremely interesting. In particular, it was noted in this paper published in Science that actually the diffusion lengths are actually very large in these materials. And, and it was there's been a bit of discussion about that. You might think, okay, well, the fact they have a big diffusion length probably means they have high mobilities. And actually, it was pointed out in this paper, actually published fairly recently, that there's actually nothing terribly exceptional about their mobilities when you compare them to other kind of more conventional materials. They're about right. And so that kind of led them to suggest in this paper that there was something else behind all of this, that there was some coupling between electronic properties and also the phonons in these materials. That theme has kind of appeared time and time again in the literature. This is actually just a paper that was published again fairly recently, I think just in December or November in 2015, where they actually do a series of calculations, some Raman measurements on actually the iodine version, and they actually suggest that there is a strong coupling between the molecular site and also the host framework lattice. So basically what they're saying is that there's a fairly strong coupling between the methyl ammonium molecule and the lead iodine framework. And they actually tie that to the electronic properties. And that can be seen in these graphs here, just from, first of all, their calculations. Here they plot phonon density of states in actually all three phases, so the orthorhombic, the tetragonal, and the cubic. And the purple spike here is actually that associated with basically the framework, the lead iodide framework. And these little green spikes are actually associated with the molecule. You can see there's actually a big overlap at fairly low frequencies here, or low energies. I might say, okay, is that actually coupled to the electronic framework or the electronic band structure, which might have some more implications to the photovoltaic properties? And there's been a number of suggestions that that's in fact true. And in particular, I just picked out this one paper here, where they actually found that there was a strong correlation between the molecule orientation and actually the band structure and indeed the band gap in this material. This is just a plot here showing calculations they've done for several different orientations. So based on this, actually, it seems to actually make sense to try to get a handle on what the phonons are doing and what the energy scale of the molecular framework is. Now, I think in this context, actually, neutron scattering can play a really strong and important role in providing information. I think that kind of for basically two reasons. One, first of all, neutrons, when they're produced from reactors or spallation sources, they have a typical energy scale of something like 25 millivolts. And it turns out, because the neutron has a mass, that energy scale actually comes with basically the right wavelength that matches real materials that we want to study in particular. So I just use this comparison here I pick 1 angstrom just as an example of a typical length scale. And if you wanted to do that, if you wanted to actually calculate the energy of a photon with that particular wavelength, you come up with an enormous energy scale, about 12 keV. However, if you do the same thing for neutrons, because it has mass, you come up with a much lower energy scale. So neutrons actually produce with the right energy scale and wavelength for the properties we want to study. Um, the other actual nice thing with neutrons, and I think it's really important for this problem, is actually they provide really good contrast of a material. So what I mean by that is that the cross-section for neutron scattering as you move across the periodic table actually it varies pretty erratically. Now, when I say that, if I understood nuclear physics a bit better, maybe I could actually come up with an intuitive explanation. But with my current understanding of nuclear interactions, as far as I'm concerned, it varies erratically as you move across the periodic table. And just kind of a nice illustration of that is this graph down here, which I sort of took from PSI's website, which is a neutron source in Switzerland. And here they actually plot the X-ray cross-section as a function of atomic number up here. So you can see it does exactly what you'd expect for electromagnetic interaction. It just grows with the number of electrons. However, neutrons, it actually varies kind of erratically throughout the periodic table. And a very interesting aspect with neutrons is the largest cross-section, or one of the largest one, actually is associated with hydrogen. And I illustrate that over here. So this is the cross-section for hydrogen, deuterium, which I'll come back to, and also carbon. But you can see that the hydrogen cross-section actually completely dominates. So that makes neutrons very sensitive to hydrogen. Usually, as a neutron scatter, we try to get rid of hydrogen because it's such a strong scatter, so we avoid things like glue. But you can use it to your advantage and study molecules that contain hydrogen. Okay, so this is actually some data that I want to start off with showing. This is actually a powder of this methyl ammonium lead bromide. So this, again, is the basic crystal structure of the unit cell. So you have your bromide framework, and you have your lead, which is these big red ions. And inside this framework, you have this methyl ammonium molecule. And what I plot over here is actually intensity as a function of temperature for taken on the ion 10 spectrometer. So what this is it's kind of a strange scan because it's called an elastic window scan. So basically, I'm integrating over all detectors, and I'm plotting the intensity as a function of temperature. And what this thing is sensitive to is basically any dynamics that enter into the resolution of the spectrometer, which is about 1 microeV in this case. Now, again, because hydrogen has such a huge cross-section, when you integrate across all detectors, you're really sensitive to just the molecular motions in this system. So you're really dominated over all these other elements. So basically what this is telling you is that, okay, at low temperatures as you heat up, there's something moving outside the time window of the spectrometer. And then, actually, at these various phase transitions, so first of all, when you go over to the tetragonal unit cell, you see a drop, so that's associated with something changing in the dynamics. And then you sort of carry on up to high temperatures. You can see that there is some action here in this sort of intermediate, what's thought to be an incommensurate phase. Now, that's pretty qualitative, but we can actually assign some numbers based on the scan. So if you plot out the momentum dependence of the scattering, you can actually extract a mean squared displacement associated with these hydrogen atoms. And that's what we've done here. Now, again, this is the mean squared displacement based on the time window of the instrument. So you have to think about the fact that on top of this, there's an energy resolution of about 1 microeV. So if you plot that mean squared displacement as a function of temperature, you see that something enters into the time window of the instrument at around 50 Kelvin. And then there's a big jump when you go into the tetragonal phase. Interestingly enough, there's nothing clearly observable when you go from the tetragonal up to the cubic phase. Now, one of the nice things with neutrons is we can actually scan perpendicular to this axis, and we can actually investigate what happens as a function of energy transfer. And that's what I'm trying to show down here in these three graphs. So first of all, if you just look at this sort of lower left-hand corner here, what I've done is I've plotted the intensity, but now as a function of energy transfer, right here, right at around 50 Kelvin, where we start seeing dynamics enter into the spectrometer window. And what you can see from this scan is that there's two components to the scattering. There's this sharp bit, and the dashed line is actually the measured spectrometer resolution. So you see something that's elastic on the time scale of the spectrometer. But at the same time, you see this very broad component here. So this fit here is actually a fit to this thing. So all I've done is I fit to it the spectrometer resolution involved with the delta function, and then something involved with the Lorentzian, basically to extract an energy width associated with this broad component that's dynamic. Okay, so that's at 50 Kelvin. Now, if you march up here, go towards the first phase transition, at 140. Now, that's actually these solid points here. So this is the same scan taken on ion 10, the backscattering spectrometer. And you see that there's actually no observable scattering. Now, if you heat up a bit into this intermediate phase, you do see that there's a dynamic component that, again, recovers. However, if you keep going, actually you find that the dynamics leave the time window of the spectrometer. So to actually understand what's going on at 140, you basically need to change instruments. You need to, okay, all right, thanks. So you need to actually basically change instruments. So this is the same scan here, actually at 140 Kelvin, but now it's done on the neat spectrometer. And the big difference here, you might notice, is this is a plot as a function of micro EV. This is now a plot as a function of millivolts. So we've basically increased the resolution of the spectrometer, made ourselves more sensitive to the dynamics. So you can see now that we can actually track the dynamics. However, the funny thing with NEAT is that, again, once you come up here, and I'll show you why in a few more slides, actually you lose all of this, and the dynamics completely leave the time window of the instrument. Now, there's a couple of things we can sort of extract from this. So first of all, we can extract the elastic intensity as a function of temperature and momentum, and also the line width of this broad component until this phase transition here, where it basically leaves the time window. And that's what I kind of summarize in this graph. Now, I know this is a busy graph, but I'll try to explain what's going on here. So first of all, what I've done up here is I've plotted the elastic scattering intensity as a function of momentum temperature, but I've now done that at two different temperatures, so at 40 and 130 Kelvin. So these are temperatures that are below this orthorhombic to tetragonal phase. And what I've fitted it to is actually, this is a fairly simple model. All it is just what you'd expect for isotropic rotations. But I've actually fixed the radius to be 1.05, and that I've chosen to be the carbon-hydrogen distance. You might say, well, this is a bit unfair. Why didn't I go out here to higher Q? And it turns out that's actually a limitation due to kinematics of the instrumentation. And also, you tend to run into problems due to Bragg peaks and other scattering processes. So I'm not trying to hide any data here. This is actually a limitation of the technique that we're using. But from this, actually, you see that, okay, this fairly simple model captures the decay, but it doesn't actually fully account for it if it doesn't come all the way down to zero. So we need a baseline here to actually fully account the data. So what we've done is we've actually modeled this in terms of, first of all, a component that's kind of freely rotating around with this distance. So that gives us this component here, and another static component that's not moving that we've called the bound component. And we can calculate, based on these fits, the fraction of the scattering that's associated with the bound molecule and those that aren't actually unbound, that are actually rotating around this fixed axis with this radius of 1 angstrom. And you come up with this plot here. So this is a log scale as a function of basically 1 over t. And you can do a fit to this, and indeed you come up with a number that's about 50 Kelvin. And that actually makes sense, because if you remember the ion 10 data that I was showing you, that was indeed a plot. It did actually show that there were some dynamics onset at around 50 Kelvin. So that seems to make sense. We can also plot the energy width as a function of temperature, from which we come up with, actually, I think it's a fairly surprisingly low energy scale associated with this rotation. It's about 2.3 millivolts, or about 25 Kelvin. Okay, so that's the story behind the molecular rotation. What I want to do for just a few more minutes is go on to, is that okay? Or how much time do you want to give me? 3 minutes? Oh, okay. 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 What I want to actually get, and there's just actually 2 slides on this because it's a fairly simple story, is I want to actually just talk now, show you 1 slide about the framework dynamics of this. So I've been talking about the molecular rotation, showing you that you can understand it at low temperatures as this molecule that's rotating around. Now, you might say, okay, what's going on with the framework? And to understand that, actually, it's slightly more complicated. You can see where you run into problems in these scans here. So these are done on MARI. And basically, what I'm trying to show you here is a comparison with calculations. And actually, the molecular and the framework dynamics strongly overlap at low energies. So the simplest way to actually separate the two is actually to deuterate the samples, to replace the hydrogen with deuterium. And that does 2 things. First of all, it reduces the cross-section, and also deuterium's heavier than hydrogen, so it changes the energy scale of the hydrogen-related modes. And that's what I'm trying to show here. So this is a plot of intensity, but now as a function of energy transfer taken on MARI. And what you can see is that upon deuteration, when you scan up to high energies, you have these peaks up here that shift and actually decrease in intensity. So they're associated with the molecular motions. But you have this thing here, which doesn't change at all with deuteration. So this is attached to the framework, this mode at around 5 millivolts. And these guys up here are associated with the molecular motions. Now, you can plot the temperature dependence of this character. What you find is that it actually softens to this transition. If you can actually fit it to a Cochrane law and find that it scales exactly what you might expect, that this is, from calculations, we know this is a zone boundary mode, and that it is associated with this phase transition. So what we see here is a softening of this framework mode right to 150. Now, one thing that is kind of interesting when you look at this is the fact that above 150 Kelvin, that you lose these nice hydrogen sharp modes, and they become very broad in energy and basically overdamped. So I just have 1 slide left. Sorry. Okay. Anyways, the energy scale of this relaxational component actually goes up to incredibly high energies. So this is again data taken on MARI. You can see that this broad component extends all the way up to 40 or 50 millivolts. Okay, so in summary, first of all, hopefully I've convinced you that the molecular and framework dynamics are strongly coupled. So at low temperatures, you have this quasi-static molecular motion that gives way to this very fast relaxational component at high energies. And that happens when the framework phonon actually softens. And so I've compared the 2 sort of different schemes, so where we've had bound harmonic phonons and also this large energy scale relaxational component. And one thing that I haven't talked about, but it would be sort of speculative, is this large energy scale in these relaxational dynamics actually associated with the nice semiconducting properties, in particular the long diffusion lengths and also the large time scales. So anyways, thanks very much.
Thank you. Very much. So we have time for 1 short question or comment. Yes, Vladimir. Yeah, okay.
Is there at least pyroelectric effect in tetrahedral phase?
Oh, sorry? Oh, pyroelectric.
It's pyroelectric effect. What about pyroelectric effect in tetrahedral phase?
Yeah, that I don't know, actually. Okay, about its pyro.
I'm not sure we measured this. I don't know.
No, we have, yeah.
And hysteresis lupna also, no?
Yeah, I don't know, actually. Yeah, I don't think it's been measured, but I might be wrong. Sorry.
I have one here, and then...
Very quick clarifying question. When you're talking about rotations, you're talking end-over-end rotations, or you're talking about rotations around the axis of the molecule?
Yeah, no. So at low temperatures, what I think is happening because of this radius is that you have your molecule, and it's basically doing this, so it's orientationally ordered. what I suspect is happening at high temperatures with this large energy scale is that it's basically doing that. It's basically gone free, so it's not.
The last one.
Yeah.
Oh, okay.
So this change in the two mode at the 150 Kelvin, how this is related to the structural orthorhombic to the tetragonal?
Oh, okay. So at low temperatures, you're in this orthorhombic phase, and at high temperatures, we think it goes free, and in this high energy relaxation core, it's gone to the tetragonal phase. And that doesn't seem to change when you go into the cubic phase. So for some reason, it seems to be that the orthorhombic phase actually traps the molecule in an orientationally ordered position. And then once you go to the tetragonal, then it becomes happy. It comes sort of free to rotate any way it likes. And that doesn't change when you go to the cubic phase, actually.
Continue on this allied structure. So next speaker is Lian Tan, and he's going to show the ferroelectric domains in these kind of systems.
All right, good afternoon. So my topic today is the same materials class as the previous speaker, except that I'm talking about the lead iodide materials, which is more or less shows the same kind of physics. But I want to look at this from the theoretical perspective. And in particular, I'll talk about the importance of hydrogen bonding and in the structural distortions in this material. So as we have heard, this material has very high power conversion efficiency, reaching up to something like 20% recently. But I think there are some questions which are not yet fully answered regarding the structure. So in some PFN measurements, you can see some sort of a ferroelectric or some kind of order at the sub-micron length scale. But at the same time, in neutron scattering experiments, like we have just heard, and also in this paper, they have shown that there is a large amount of molecular disorder coming from the rotation of the molecules. So in this talk, I would like to address basically the energy landscape of this material, given that it's very complicated at the low energies and it has many multiple small barriers, and how we can understand this in a simple way. So I'll just briefly go through the phases again. As we know, the low temperature phase is orthorhombic, same as in the bromide structure, and then it becomes tetragonal, and finally the high temperature is cubic. Perovskite structure, the inorganic part is perovskite, and the organic part has some, in this case, CH3 and H3 molecules arranged at the A site. Early DFT calculations have proposed two types of modes of bonding of the molecule to the inorganic cage, corresponding to the orthorhombic and tetragonal structures having different types of hydrogen bonding. Basically, if you look carefully, you can see that the hydrogens are bonded to different halide sites in the two structures. But let me point out that these DFT calculations were done at 0 temperature. And as we know, at higher temperature, the molecules can be rotating. So the picture is actually probably much more complicated than just two types of modes. But exactly how much more complicated? So in these neutron scattering studies, they have shown that there are many types of molecular rotational modes, and also, like we have just heard from the previous speaker, there are actually many possibilities in which the molecules can point. So it's likely that there's not just one single favored hydrogen bonding mode. In this somewhat more recent experiment from last year, they have shown actually in the tetragonal phase, they think that there are 4 possible orientations of the molecule corresponding to 4 faces in the tetragonal cell. And in the cubic phase, basically, it can be pointing anywhere. So with that as a prelude, I would like to address the following questions today. So what exactly is driving the interaction between the molecules and the inorganic cage, and what's the nature of the coupling between the two? And how can we understand this in a simple way without having to do very, very long like MD simulations? And are there any simple rules we can understand this structure? So this is my approach to this question. I basically want to sample the low energy landscape. So I start off theoretical DFT calculations in some random orientations, I mean the molecules pointing in random positions, and I let it relax to its ground state or close to ground state structures. And in so doing, I build up a database of energies and structures. There are about 200 of them, and I start with randomizing the positions of the molecules, including the hydrogen positions, because I want to know, I want to sample the hydrogen bonding patterns as finely as possible. I've used PBE density functional with the dispersive corrections for van der Waals forces, and this was done in a 2x2x2 supercell. So before I talk about my results, I want to explain how I can derive some kind of useful statistics from this sort of database. Now, so the first thing I want to look at is the hydrogen bonding. Now, if you take a very simple point of view, the hydrogen bonds from nitrogen are going to be stronger than those from carbon. So in this figure, if you look carefully at the distance between hydrogen and halide atoms, they're a lot closer for the ones on the nitrogen end than on the carbon end. So one simplification I'm going to make is that we can ignore those hydrogens on carbon and just look at 3 hydrogen atoms per molecule and categorize where those guys are bonded to. Now, if you look at a single hydrogen bond, most of the time, one hydrogen bonds to one iodine, in the sense that if you collate all the distances of the hydrogen bonds, there's one which is very much shorter than the rest. But there are some cases where there are multiple hydrogen bonds very close in distance to each other, like this one, for example. There's 3.52 angstroms here and another 3.5 angstroms. So some cases, there are multiple bonds. So how do I handle this? Basically, I abstract these bonds out to a problem of choosing edges on a cube. So if there are 3 hydrogen bonds, meaning that all 3 are singly bonded, I'm basically choosing 3 edges on a cube. And if there are more, I can choose 4. Very rarely there is 5. Most of the time it's 3 or 4 for the structures in my database. So I'm explaining this kind of notation because this will be the degrees of freedom in my effective model, which I'll explain later on. Now let me explain results of DFT calculations. Now the way you read this histogram is like the following. So I have many structures, and each structure has a certain number of bonding modes. Now for each bonding mode, I take the energy corresponding to that structure and put it in the appropriate bin. And what I find is that there is a predominance of 2 or 3 different types of bonding modes shown here. So for this type of bonding mode, is basically all those counts which are labeled in green, and these ones are the ones in blue, and these ones are the orange ones. These 3 are the main ones in the sense that they account for most of the bonding modes in my database. But there are some others which I've not labeled here, but these happen only at the higher energies. Now, if you look at the very low energy structures, it turns out that all the hydrogen bonding modes in that structure have only one type, and it's this type. And actually, this corresponds to the orthorhombic phase. So all these structures in here, all in the orthorhombic phase, and there's an energy gap between here, between the structures here and those in the higher energy manifold. One thing I would like to point out is that even though this particular type of bonding mode is completely dominant at the lower energies, it continues to be very favorable even at the higher energies. So if I want to make a model from this kind of data, it makes sense to include this particular type of bonding. Now that I've addressed the hydrogen bonding, next I want to kind of explore the distortions of the inorganic lattice. Now I can think about this in a simple way. So basically, each iodine atom is surrounded by 4 cells where it can make hydrogen bonds to. So going back to this notation, I can think of a possible inorganic distortion as putting arrows on each of these edges. And each of these arrows can point in one of 4 directions. Now, if I count the total number of possibilities, it's a very big number. Basically, I have 4 possibilities per iodine, and it's a 2 by 2 by 2 cell, and there are 3 iodines per cell. So there are a lot of them, and even accounting for symmetries, there are still very many, but I've tabulated all of them in the database. And it turns out that even so, there are still only a dominance of a few types of bonding patterns. Basically 2 or 3 types. Now, if you look at the most prevalent ones, the most stable one is A minus C plus rotation. It's coming in the orthorhombic phase, and it's completely dominant in that phase. The other types of distortion patterns are not purely rotations. They contain some sort of ferrodistortive modes. And those are the blue and orange ones. And there are also somewhat more different types of distortion modes, which include ferrodistortive displacements, especially at higher energies. Now, finally, I would like to explain how we can construct effective Hamiltonian from what we've just learned. Since the molecules are dipoles, they have a dipole moment. There should be a term in the effective Hamiltonian which is an electrostatic form, and this part shouldn't be surprising. But there is also a short-range term which comes from a coupling between neighboring molecules. And at first sight, it's tempting to use some kind of simple formulation for this short-range term, like a vector-like coupling, maybe like a dot product between the orientations of the 2 molecules, for example. But actually, that's not an appropriate description. I found that the better description is to use these types of bonding patterns as variables in the effective model, and introduce couplings between different types of bonding patterns. So one example is shown here. You have a red type bonding pattern with this orientation, coupled to a blue type bonding pattern with a different orientation. And for each possibility, there's a different coupling. And so I've implemented this model and fed it to my database. And I get a somewhat reasonable fit, I would say. So this is over the entire energy range of the database. And I would say that it correctly predicts what the ground state structure should be. So these points here are actually the orthorhombic low temperature phase. And that's predicted correctly by the model. And I achieve like 7 MeV root mean square error. Now, if you compare this to a very naive model where you use a different coupling, like a dot product vector-like coupling, like this, that kind of model fails miserably. You get a much larger RMS molecule, and even the ground state structure, which is predicted, is wrong. So with that, maybe I can make the conclusions. I hope to have shown today that there are two factors which are important in this hybrid perovskites. The hydrogen bonding and the presence of lattice distortions. Now, probably the point that I would like to make today is that the short-range coupling is actually of a complicated form, and it's not a vector-like coupling. One has to be careful to take into account the proper nature of hydrogen bonds. We're doing right now Monte Carlo simulations to examine how this plays out in finite temperatures, including dynamic disorder. Now, before I conclude, let me make a small advertisement for a poster, which is about the electronic structure, which I didn't get to cover today. It's about how the electronic structure, how the structural properties and the spin-orbit coupling affect the long carrier lifetimes in this material. So thank you for your attention.
Time for question, comment. We start with Vladimir.
Dr. Tan, is it really a relaxer?
I don't know. So I will do this Monte Carlo simulations, and from that I hope to find out more detailed information.
Yes.
Really relaxer?
Yeah. Yeah, so I would say that in experiments, you can see some experiments show some domains. And in the theory, of course, you can make it ferroelectric. You can do it at 0 temperature. You can put it in a ferroelectric arrangement like this. You can put it in a ferroelectric arrangement like this. But I would say that in reality, at room temperature, it's not a true ferroelectric. You don't get like a very large scale macroscopic domains. You get a lot of fluctuations in the orientations of the molecules. And I would say that the dynamics of this process is very important. Now, having said that, I would not rule out the importance of some kind of dynamic pseudo ferroelectric order which contributes to the light, the power generation efficiencies of these materials. There are experiments which show that if you shine light on this stuff for a long time, the photo current goes up and up, and that may be attributed to increased order coming from exciting the molecules into more ordered states. So I would say that it's not completely clear yet.
Okay. No more? Charles?
Do you know the exact space group at room temperature of this compound? Because the previous talk showed that there was like PNMA, E4MCM, and PM3M, which are all like centrosymmetric space groups. Since it's been shown that the BPVE, for instance, is a further order tensor, it should vanish in this case because there is central symmetry. So do you know the space group of this compound?
Right. Yeah. So you're right. So in PM3M, we don't get any the bulk photovoltaic effect. But in something like this, for example, where you notice that the molecules are kind of partially aligned, and there'll be a net dipole in the 001 direction. Something like this would actually give you a BPVE effect. In this case, not in this particular case. It depends very much on the orientations of the molecules.
Antiferroelectric, maybe.
I'm trying to connect yours and then the previous neutron study. So do you find any differences in the bonding character between the, let's say, hydrogen and then the inorganic site according to for the different like tetragonal orthorhombic and cubic phases? Have you find some difference in character in bonding between hydrogen and then the inorganic atoms?
So if I understand correctly, you're asking if the bonding in the tetragonal phase is different than in the cubic phase. No, I have not looked very carefully at the bonding in the cubic phase because for my energy structure database, I was actually using lattice constants more comparable to the tetragonal phase. So I don't really know what the bonding is like in the cubic.
The organizer will kill me, so let's. Okay, next speaker, Ron Cohen, on oxide nitride perovskite, synthesis and characterization.
So, where's the mic?
Is it the correct title?
Where's the mic?
Oh. Sorry.
That's okay.
Okay, great. So it's been at least since 1990. Somebody correct me if we met before that, but I don't think I've ever given an experimental talk. So I thought it was about time that I learned, how easy it was to do experiments, so I could understand why, in what way I could stimulate my colleagues to work a little faster. So I've learned my lesson. Okay, so I actually will give some theory towards the end on something else. So the people that really did the work, though, are in the pictures here, and I just kind of operate the driving force. So the first author is Mukhtar Ahart, who's really the spur behind this effort. And I'm going to talk about some new oxynitrides. Is there something wrong?
No, it's okay. Just
okay. And how we finally made them. And we predicted these. By the way, people have asked. So this is also Carnegie. This is our laboratory, but it's across town in Northwest DC. So you were kind of wondering where the labs were here. But we're not having a tour because it's quite a drive up there, even though it's not that far in miles, but it takes a while in traffic. So this is work that actually did with Razvan Karakas, who was a postdoc at the time, and we made some predictions based on a perovskite structure like this, where you replace 1/3 of the oxygens with nitrogen. So you make an O2N oxynitride. And the question was, just simply what happens if you replace an oxygen with a nitrogen? Now, it's very easy to do on the computer, okay? So on the other hand, it's still a lot of work because we basically went through a large amount of the periodic table, and we had some criteria. We looked, so this is a kind of review. Maybe I gave this talk, 15 years ago or something. Well, actually, it was published in 2007. Okay, so this is going on 10 years since it was published. We looked for materials that were stable, that were insulators, and that had a high polarization. So basically, we would put in a structure, just pick A and B to be two elements out of the periodic table, and then put O2N, and then try to optimize the structure as a perovskite. Many things just fell apart, and we didn't try to see what they might go to, but if they just fell apart and didn't look anything like a perovskite anymore, we just quit. We looked for things that were insulators because we were looking for something that might be polar, and so if it came out metallic, we threw it away. And then we were looking for things with high polarization. Now, there are known oxynitrides. In fact, you may remember transparent aluminum from Star Trek. So there is transparent aluminum. It's aluminum oxynitride. So there are known, which is a transparent metal. There are known oxynitrides. There's a famous oxynitride that occurs in in meteorites with silicon, but it's not a O2N. I guess it's N2O. But it has a mineral name since it's found in nature, cynoite. But generally, there's been a large effort in the materials world to make oxynitrides for a lot of reasons over decades, but none of them, well, except with some recent exceptions that I'll show you, have really been polar or possibly ferroelectric. But anyway, at the time that we did this work, there were none that were known to be polar or ferroelectric. We came out with two that seemed to be very promising, yttrium silicon oxynitride and yttrium germanium oxynitride. And they both had strong high C/A ratios. Of course, we put them in as ordered structures. And they had very significant, I'll show you some of the properties in a minute. And, I think this is one of the, even though it doesn't really get credit for it, well, maybe because it hadn't been made, but, it was one of the first really materials by design approaches that Razvan started with me, where we were really kind of methodically trying to come up with new materials using density functional theory. Now, some things didn't work. They may still be interesting materials, but for example, here's kind of a counterexample. If you take Indian titanium O2N and you start with something like this, it actually kind of falls apart and makes tetrahedrally coordinated ions. Looks nothing like a perovskite. It could be very interesting. I mean, we actually calculated the properties of this material, but it's not a perovskite, so we kind of didn't follow up on it any further. But there may be other interesting materials as well. So anyway, these two materials, we basically went through and applied all the new technology of the day to calculating its properties. And we calculated, for example, the polarization. So we heard a talk yesterday about a more straightforward way of doing that, which is good. But you see here we used the old-fashioned way of actually tracing out these different polarization branches so that we could see exactly what the polarization was. The polarizations came out so large that you really had to take some care to do this properly, because we actually got the largest polarization, I think, of anything known, at least at the time, and maybe still, for this yttrium silicon oxynitride. So these were very large polarizations and very significant effective charges. So the effective charge on the I mean, not hugely anomalously so. I mean, actually, I guess they're not that surprising numbers, but nevertheless, it had very large displacements, a very large C/A, and a large polarization. Let's see. We looked at a lot of different things to try to see what might be useful other than the polarization. And it turned out that the one property that really jumped out at us were the nonlinear optic coefficients. And I haven't really compared them to KTN because they're in a different form, and I haven't really figured out how to do that. I should. But these are basically third derivatives of energy with respect to electric field, and the numbers that we got for these materials were as big or bigger than the best nonlinear optic materials that were around at the time, like KDP. So it could be a useful nonlinear optic material, and so it would be nice to make it. We did find that it would be stable if you could just get the atoms in the right places. So we calculated the phonons for these materials and found that they were all stable. We calculated the phonon frequencies, and we figured that this could be a useful blueprint for discovery. So all those years since, I've been trying to get people to make it. I did hear some kind of apocryphal story that somebody blew himself up in St. Andrews trying to make it, but I don't know if that's really a true story or not. We suggested in our paper that it be made by mixing together yttrium nitride and silica glass. And yttrium nitride is an unstable material. I think it's actually a controlled material because it's explosive, but we did manage to get a hold of some, and it's been sitting in a desiccator in our lab for 8 years or something, and still wasn't able to get anybody to try to do it. This shows what even my own colleagues think about theory and theorists. Why waste our time doing that? But anyway, in the meantime, some actually possible ferroelectric oxynitrides were made and published. And I think this kind of stimulated me that we should go back and really try to do this, because this material that was made, the strontium tantalum O2N, which is perovskite-like, I'll show you some of their results for it. Really, I think ours should be better than that. What they found is that they usually got this, what they call cis type of nitrogens on the octahedron, so that they're stable. The most stable phase is not ferroelectric or polar in their case. It would be like anti-ferroelectric, centrosymmetric. But they suggested that there could be this trans type where you have a polar structure. And they showed some evidence that in little domains they would get a polar structure. And with the piezo microscope, they were able to do some noisy-looking loops and even write some patterns onto the material. And they did some calculations of the polar structure, and it was higher in energy than the others, but they suggested that it might form just a kind of a disorder. I should mention that traditionally oxynitrides are made by an ammonization process where people take an oxide and they react it with ammonia. And there's many, many groups and people all over the world doing that for decades now. And they make many interesting materials, but the problem is it's a low-temperature process where the nitrogen goes in randomly for the oxygen, and you don't end up with a polar structure. So in this paper, they use pulse laser deposition. They put down layers of material. And in fact, I have a collaboration with a group in Japan which tried to do this for this material, but I think never got any, well, the problem was getting the proper nitrogen targets and so forth. So there's still a role for doing that. We did get a couple patents on the material, so you can get a material patented just on the computer. And Carnegie always wanted to know why no one wanted to license it from us. And I said, well, probably they want to see it sitting on their desk, not on their computer screen. So we really needed to make some for people to look at, So here we go. We have to work in a glove box because the yttrium nitride reacts with air. And so thanks to O&R, thanks to Wally Smith, we got some funding to start a small experimental program and try to make it. And my colleagues all like to do things under pressure. And since it's reactive in air and everything, it seemed like a good idea here is that you could load a diamond anvil cell inside the glove box and you don't have to worry about reacting with anything. And we know that silicon generally wants to be tetrahedrally coordinated at low pressure. It seems like putting a little pressure on might help make it want to be octahedral. So it seemed like a good idea to start out that way. So we're putting on pressure just by applying two diamond anvils against each other. And we also heat. Okay, when it turns out that nothing happened when there was no heating, so we heat with lasers. So you use a laser to heat the sample, and then and that's basically a picture of the apparatus then for the laser heating and pressure. So this is equipment we already have for doing high-pressure studies. It's not like we went out and built a high-pressure lab. And you may have seen this out in the hallway. This has nothing to do with this experiment. And Tim Strobel, my next-door neighbor at the lab, is not involved in this particular work, but it's just such a cool photograph. So basically, this is a fake photograph anyway. They just turned on all the lasers in the lab, and pretended that they were doing science. So it was really art, art. So anyway, so in the process, I'll show a picture in another picture in a minute, but we actually did make this material, and my group made it, and our colleagues made it, and so there was excess silica in this particular experiment. It turns out that maybe there's another route to making it that's easier. It turns out that the yttrium nitride is not that easy to work with. It's like little flakes, and they're very non-reactive. Yttrium nitride turns out to have this huge melting point. So even though it's reactive with air and water, to melt it, it's one of the highest melting point materials around. So it's not very reactive, really. And so what was done is to sandwich it between some silica glass, and then one ended up with excess silica, and all of the yttrium nitride reacted to make this oxynitride. And we have the X-ray pattern, and we computed, originally the CNA parameters and compare those with what are measured under pressure I actually didn't go back and compute them under pressure, but probably the synthesized material isn't perfectly ordered. It probably has a little bit of mixture of oxygen and nitrogen, but definitely you see this strong C over A. It's definitely layered. It's not cubic material. We maybe even more encouragingly measured the Raman, and even though it looks very messy, you can see where the peaks are, and if you compare the numbers, it's much, again, I'm getting reality tests by trying to be involved in this experiment, right? So you know, as a theorist, everything should just be clean like this table over here, you know. Who wants to look at this? You know, just look at the nice numbers. So, you know, it's pretty good agreement of, you know, within, you know, 10 or 15 wave numbers of the theoretically predicted frequencies for this material. So it looks like we really made it. But the real test, then, is it a polar material? Because there really are not many known polar oxynitrides. So we did second harmonic generation measurements. And by the way, this is a picture of our sample. So this is not like a nice cube for Wally Smith to sit on his desk yet, you know. This is 300 micron sized crystal, you know. So we'll try to make that big cube, but, you know, we're going to have to use some other method. So we measured the second harmonic generation in a centrosymmetric material that would have no second harmonic. Oops, what happened to it? The data's not here. Anyway, we got a nice peak. You'll have to take my word for it. Somehow I took it out. Wow. Okay, I'll show you later. So somehow I just included everything but that. Anyway, just imagine a nice big peak, okay? You know, so we got a second harmonic generated signal showing that it was polar. Okay, so we've made the material. We want to make bigger samples, so I think we're going to try to make the germinate next. Generally speaking, germinates are easier to make than silicates, and hopefully we can make a bigger sample and maybe even make it at ambient conditions. So in the last bit, I want to talk about some theory, which I think is exciting, and this is, I'll call it, Wally said I needed to have a good name for it. I don't know, defect dipole enhanced piezoelectricity. Anyway, there's a number of people involved in this again, and both from, again, it's not all theory. We're doing experiments also, so I'll show you some of the experiments as well. So this goes back to, this is from 1972, a paper by a guy named Jonker. Does anybody know him? I don't know him. Anyway, he showed this really neat thing. This is just barium titanate, and he got these double hysteresis loops when he aged his samples. And he said it was due to defect ordering, probably. And then it really wasn't picked up on for a long time, as far as I can tell. And it looked kind of interesting. And then there was this paper by Wren many years later. Where's the date? This is 2004, okay, where he showed a really enhanced, well, first of all, he showed these double hysteresis loops and everything, and then he showed a greatly enhanced piezoelectric effect caused by this, and I'll say more about that. And for a long time, I was going around telling people, could this possibly be correct? Because nobody else has gone and reproduced this work. And I was about to say that here at this meeting, you know, because I stopped doing literature searches for it maybe a couple years ago, and, you know, when I was basically finding nothing. So anyway, so I checked like yesterday, and I found that there's been like 400 papers published in the last year, you know, most of them in China, you know. So people have finally rediscovered this effect, and here's a paper published, for example, in 2015 showing the exact same effect as that Jonker paper. By the way, one thing that might have discouraged people, I don't know if this was just the norm back then, because I was kind of in high school, but in this 1972 paper, he says he aged the sample, but he doesn't say what that means, like was it hours, days, minutes, or whatever. He has some temperatures here, but note the graphs here. It says time, doesn't tell you how much time, and temperature, I guess it does show you the temperature. But anyway, you know, not a lot of information. I have a feeling that was done, you know, because maybe it was going to be something useful. And so they wanted to publish, but they didn't want to give you all of the details. Anyway, here you see you start getting some numbers. So it says 8 days. So, I mean, it really is waiting for a while. So here you have a process in the material that takes days before a change happens. Of course, the temperature is fairly low, like 70 degrees C, but still, over a period of days, things are changing. And this is the thing that really excited me about it from Ren's paper, from Ren's work back, over 10 years ago, is that you get this tremendous enhancement in the strain and in the piezoelectric coupling, which is basically the slope of these curves for these aged samples compared with the unaged ones. And he had I've enhanced this a little bit, but basically this is Ren's idea of what was happening here, is that you form defect dipoles in the sample that give you, and then during the aging process, they line up with each other. By the way, you're going to give me a warning in time? Okay, 5 minutes. Okay. So during this aging process, the dipoles line up. And then you, even though he was not really explicit in his papers, it only makes sense if you apply the electric field then perpendicular to the polaring direction. And then what that does is it rotates the polarization, and then since during that process the defect dipoles don't diffuse, the atoms don't actually move around, you have oxygen vacancies and so forth, and so they end up remaining in there in the original, up position. So then when you remove the field, it rotates back again. So you have kind of like a polarization rotation effect that's reversible. And so this is the kind of thing you would expect to see then, just a schematic I drew of, and this basically is that double hysteresis loop that's seen during that rotation process. So we've been trying to look at this both with theory and experiment, and as usual, the theory's harder than I wanted it to be, and the experiments, of course, they're much harder than I wanted them to be. But anyway, that's life. So this, for example, is calculations that a postdoctoral associate at Carnegie is doing. Hero's doing this with me. I'll show you more in a minute. And so this is like a 2x2 supercell, 2x2x2 supercell perovskite done with DFT with a manganese replacing one of the titaniums and then an associated oxygen vacancy. And when you do this then, and we doing it for bigger supercells as well, what you see is you can calculate like a perfect hysteresis loop, and you can see that when you put in the defect dipole, it's displaced. And you can calculate this in different ways and try to estimate what the effective bias field is in the material. And for example, this is showing the polarization versus applied electric field, and both with and without the defect. And you can figure out that basically all of these different methods give the same number, about 20 megavolts per meter. Now that sounds huge, but that's for basically like 12.5% manganese. So that's more manganese than probably would be soluble. Well, from our experiments, you can only put in a couple percent. So for 1% manganese, it would be 2 megavolts per meter. So it's still an appreciable bias field, and with 2%, I guess it would be double that. And also, this is work by Shi Lu. Again, you heard his talk earlier today, but he's doing this work as well. This is for potassium-doped barium titanate, and so it's a little bit more complicated structure. You have 2 potassiums and an oxygen vacancy, and in a 3x3x3 supercell done with DFT. And again, what you find is that you can actually put on an electric field, drive the polarization so that it switches from the Z direction to the X direction, so you're putting on a perpendicular field to the original polarization. Then if you actually turn off the field, then in DFT, the polarization actually switches back. So you can see this rotation effect directly. Of course, this is at 0 temperature. This, let's see, this is the same sort of thing, but now for potassium-doped lead titanate. The problem that we had in the case of the barium titanate is that, barium titanate, as you remember from the 20 workshops 20 years ago, has this 8-site sort of potential surface. So it's not a simple tetragonal structure, and so at 0 temperature it's kind of complicated by these saddle points and these multiple minima. But lead titanate just has a single minimum, so it's a cleaner effect. And on the other hand, it's not really switchable in experiments. So, but we can do it on the computer. And so this shows this process of applying an electric field. This is the strain shown here, but there's a similar graph for the polarization. So basically, you switch the polarization so that it goes in the other direction, and then it goes back spontaneously. So we see here recoverable strains of like, if you could actually do this, of like, over 10%. So, that would be pretty amazing if it was really possible. So what about finite temperature and larger systems? So Shilu's been using this model developed at UPenn with Andrew Rapp's group for very large systems. And I don't think that's written. Oh, here it says supercell with 1,000 unit cells. Okay, and the idea here was just put in explicitly. 1 minute. Okay. Explicitly defect dipoles, but actually is just a Coulomb potential, just to put in the dipole. And then see what happens, see this effect. And we see the effect, and you can see it switching and switching back with time. And I don't have time to go over this in detail. Obviously, this is work in progress. But what's very interesting is that you can then look at different simple things and see how it affects the behavior. For example, you can change the size of the dipole. And interestingly, the change in the coercive field doesn't change much with the change in the dipole. Once you put these defect dipoles in, that suggests that it's not really that sensitive to what the chemistry is. It's really just a matter of having the dipole in there, and it doesn't even matter exactly how much it is, as long as you've got the bias there. What was much more sensitive, though, was to the amount of the dipole. So if you go 2%, 3%, 4%, there's actually very large changes in properties. It's very interesting here that you have, these huge changes in properties with just change of 1% of defects. And so, in real materials that you buy from a company or something, there very well could be 1%, that we know that they throw manganese in and so forth. So the actual materials that are being used in applications really have this stuff in them, and it could be affecting the properties that are being measured and used. And just in the last slide, we're actually doing this in the lab, and I really don't have time to talk about it. We haven't yet done the exact experiment that I want to do, which is the one that basically mimics what we've been doing on the computer. But we do have some measurements showing effects of aging, and they're really in process. This is work of Raja Vadapu, again, a postdoc funded by ONR at Carnegie, and in collaboration with Peter Finkel at the Naval Research Lab. So in summary then, I talked about two different things: synthesis of new predicted polar oxynitrides, and the beginning of a theory for the defect dipole-enhanced piezoelectricity, and the beginning of experiments on the same thing. Seems to be a real effect. Okay, thank you.
So I was just wondering, in your first principles calculations on the defects, what charge state you assumed for the oxygen vacancy, and in the presence of all these fields, wouldn't you expect the charge states of the vacancy and its complex with other atoms to change?
Well, we're putting in, completely charge compensated systems right now. So, putting in like Mn2 plus for Ti4 plus, and then an associated, oxygen vacancy. So, I mean, we've done some other work that certainly seems to be the most stable situation. But, in real life, you could have other things happening. In fact, even manganese can take on, multiple valence. So that's actually another thing that we're working on. But I don't have results to talk about today.
Last one? No? Coffee break is needed.
Okay, thank you.
Thanks, Ron. And all the speakers, and any comment? Nothing? It's okay? Okay. 20 minutes break.
Okay.